Coming back to the wood story. Now, that's an image of what you expect to see if you got some seismics in which you want to amplify the brightness or amplitude value. So this is what we call RMS visualization of the seismic. So visualization in which you are looking the root mean square of the amplitude. So you are boosting the amplitude into the seismics versus the characteristic of the reflector. To give you an idea what we got, if we are lucky and a certain depth in terms of reflector, so what my difference in contrast of impedance between the two objects is giving in terms of seismic is that one. In one reflector, you got all that stuff that you can see in the well. So the reflectivity we are speaking about is a kind of rough approximation of a huge word that for a sedimentology is a huge word. So sometimes the reservoir can be big as your reflector. Sometimes you don't have something like that, but you have everything more shortened in which basically all your only using one reflector, so you got a black reflector and black green, and that's it. And then you are in trouble because you have to use and study your basically reservoir that is confined in a one single reflector because the dimensional reservoir is 5, 10, 20 meters. Most of the job needs to be done through wells, taking and interpreting the lateral variation of the amplitude. That case is the lucky case in which you got a big reservoir. So I can not say a giant, but a good reservoir. Okay. Now, coming back to the story, when you're interpreting seismics, you're interpreting a stacked seismics. So we are going to see what are the implications. When I speak about stacked seismics, I will describe you later what does it mean. But basically, you are basically doing a summation of reflection that you are assuming they are doing a common midpoint reflection into a point that you are stacking all together to kill the random noise and to amplify the property related to the amplitude. So this is an image from a stacked seismic. This is the seismic usually you use to do interpretation. And people, especially ExxonMobil have a bit of obsessionate on classifying things, on showing their own way to the world, what it should be, what it should not be. Usually are pretty good, because ExxonMobil got a kind of research group that is a tremendous research group. Been lucky a couple of times to manage with them. They know what they are doing, but they like to run the world. So what they do, they produce a series of papers in which they show how we should classify the various types of contrast of impedance and amplitude variation, amplitude property, observational things, and you can relate them to basically the contrast of impedance. As you see, they describe the amplitude as a high amplitude with strong continuity, high amplitude, low amplitude, strong continuity, semi-continuous, high amplitude, non-continuous amplitude, and then the mounted and unmounted. Now, if you want to interpret those reflections in terms of the contrast of impedance, that's now pretty easy. The first one is telling you that the contrast of impedance of these two units that are visible at the seismic scale and are producing a reflector on the seismic scale are pretty much constant. So it's telling you that there is no real change of the contrast of impedance. Laterally, they are bright, so the difference between ρ2 V2 and ρ1 V1 is pretty strong. So there are two objects with a kind of distinctive contrast of impedance, constant laterally for kilometer and kilometer. And that's the only thing you can say from a seismic point of view. You know that, well, you will see with Nick Schofield that most of this kind of environment are related to a kind of turbidite. Flat turbidite deposit, everything is fine, no strange kind of geometry, so quite far in the middle of the kind of a basin in which you got a strong transgression or regression, basically things happening. From my point of view, pretty boring. But from your point of view, if you're looking for oil and gas, it's a good place where to go. In that case, you don't have real bright spots because they're all the same. Okay? The one on the right, that one, is telling you that you got an alternance between bright, strong reflector and a series of very continuous reflectors by which the contrast impedance is not that strong. So it's telling you that the objects inside are continuously constant in terms of contrast impedance, but the brightness is not great. So that's what I mean when most of basically the brightness is not preserved because most of the reflection is lost into transmission. Go below, 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 below. Usually, the reflector that if everything is okay, you don't have any pockmark, any basic localization of gas or any kind of basalt intruding into the seabed, usually the seabed is a really bright reflector, constant laterally. And the reason because it's a contrast between water and any kind of rock below. Any kind of rock below has got to have a velocity and a density that is bigger than the water density, is bigger than the velocity of the water. The only case in which you got something that doesn't work well is in the case when you got basically something like that. You see that? That's pretty shitty from point of view, but it's beautiful from a geological point of view. It's telling you there is a lot of fault and localization of brightness and lose of amplitude laterally. It's telling you there's something happening in the seabed. So probably you are in a kind of rifting condition that is breaking up through the faults. Rifting implies that you have a hydrothermal fluid that are coming up, pockmark, basalt. So we have a fast change laterally of the amplitude that are destroying the continuity of your seabed. Okay? Usually the seabed is very important. You will see why. Because if everything is okay, water into a regular, basically, hemipelagite that are doing the first contrast of impedance, you can define the polarity from the seismic data set without asking to any kind of processor. Because we expect to have the amplitude of the seabed to be necessarily a growing polarity. Because you go necessarily from water to rocks, and there is no doubt that should be a peak. So, if you know there is a peak, because the seabed should be a peak in a regular condition, I repeat, you know if the black and the red color that the company is using, so the black color in that case is the stronger reflector, represent a peak or a trough. In that case, the black one represents a peak. And this is, by definition, we're going to see how it works, is the little bit trough below and the trough after that you expect to have in any kind of way. But the strongest reflection need to be in a seabed, the peak. Then you understand if they're using the rules of the American rules in which you use the peak as a black color, or they're using European rules as the peak, the red color. Of course, the two continents, they never agreed on these kind of things. Once you know to work out, the only place where you can securely fix some answer about that is the seabed, because you know exactly what's on the top and what is going to be below. Okay? Laterally, well, as you see, you get then all a variety of laterally basically changing amplitude. So in that case, the semi-continuous, in that case, reflector, those kind of object there, it shows you that if you want to map that reflector, whatever you map on the red, you map on the black, it's laterally missing the amplitude. So we have a fast laterally change of a control of impedance between the top and on top or below. So it's telling you that there is some kind of content inside the unit that is a continuous reflector, kind of continuous reflector. In some cases, it's disappearing. So in some cases, you don't have a proper reflection. So in some cases, the two contours of impedance are so equal that you lose a lot of amplitude laterally. So something is happening there. A good interpreter is saying, what's happening there? That is something similar to that one, in which you got strong reflection on top and the bottom. Okay. Oh, that one is a kind of section of a channelized structure. Channelized object are those kind of things there, and the channel are coming more or less in that direction. You are cutting off through with your seismics, and you are seeing basically all this lateral change of amplitude with this kind of V geometry that look basically the scar of your channelization. That one is an example in which you got all the object inside. You got strong reflector laterally continuous, strong reflector laterally continuous, and a lot of super stuff with the kind of intrinsic feature that you see inside. This is typical of the mass transport deposit. So this is a mass transport deposit because you got the shear plane on top of that, the shear wheel on top of that. So this is the place where you got, when you got a mass transport, you got a massive amount of conglomerate and material that is basically flowing down, depending if it is a fluid sustaining, grain sustaining, or the expert on turbidite. I got all this kind of detail about that. At that scale, we don't care, but we know that when it's flowing is stacking the material at a certain point. The stacking material, if you cut them, they got this kind of stacking geometry. Look like a small thrust, but the scale is telling you, you don't have the scale, but trust me, the scale is telling you that you need to be a kind of transport deposit. But the classical thing of transport deposit is that just below the first material that has been flowed, and it was rich of fluid, and just on top of the last event, you start to have a kind of discontinuity with a completely different material that are transgressing on top of it. So you should expect to have on top and on the bottom strong reflection, and in the middle all the geometry that characterize the mass transport. As you see, that's where the geological understanding that you got is going to overcome the understanding of a geophysicist. Because a geophysicist, if he doesn't know what is it, the mass transport, he starts to map that stuff, trying to find a way to connect this kind of reflection. And you look at him and say, are you crazy? Because you are connecting something that cannot be connected because they have mass transport deposits. So the only thing you can map is the reflector by giving them the real geometry that they got, because we have seen it. So that's where the interpretation starts. The only place where there is no discussion about the continuity is that one. And that one. Strong amplitude, low amplitude, and lots of discontinuity. So there is a clear change of lateral behavior and geometry of the stacking object. The contours impedance is in fact controlled by the geometry of the reflection and the variation of the contours impedance basically. Right. Those are the situations. That's another example of stacking material across a mass transport deposit. Top, bottom, and all the stacking object in there. You see this kind of stack orientation is telling you that the transport was in long direction. Well, that's the way they are stacking, and what you see is the stacked unit geometrically showing their representation and their reflection. So in that case, unit, a unit, a unit, a unit, or at least a visible unit at that frequency, a visible unit at that frequency. Okay, so the reflection can be interpreted back to the concept of the contours of impedance. If you are particularly unlucky and you got something like that, well, that's typical in place where you got a huge amount of reflection that are being devastated by a kind of gas transport across the object. So you have a strong fracturated area filled by gas, so it's a hydrothermal component, and those ones are lowering extremely, are devastating, if you want, the contours of impedance of the original unit. The understanding of this physics, I will show you when we are going to look at the contours of impedance more in details, has been well understood with the 4D seismics. Right? The people start to inject fluid into a rocks. They did the seismic before injecting, during the injection, and after the injection. And you realize that the contours of impedance is perfectly thriving following the formula that we have seen. You got the fluid moving, so you see the contours of impedance changing through the fluid it is passing through, and when you do the photography during and after, you see the variation, the localization of the bright spot as far as the fluid is filling basically the reservoir, and is changing the relative contours of impedance. So those things we are looking at, they are tested using experiments, so it's a fact, okay? Perfectly explained by the theory that is behind that. They come from the equilibrium between the stress-strain field using the elastic parameter, etc., etc. Okay? Problem, practical use of the impedance. That's the problem between the seismics. European use basically, if you got a contours of impedance that is increasing, so you are physically water seabed, okay, classic water seabed. Well, that's the way the European, they used to describe a peak. That's the way the American used to describe a peak. The only way to do it is that if you are using Petrel, you go back to Petrel. There is an option that gives you, within Petrel, to map using trough. You click out mapping using trough or peak, one of the two, and then you go back to the seabed and you see which is the color that the petrel using that seismic, so using the ZY, is giving to the peak or to the trough. What you can do now with petrel, you can change the color. So if you are annoyed with your American, you want to see that one instead of that one, no problem. You go to the petrel, switch the color, and everything is sorted. But once you are using peak and trough, you are forced to use your decision throughout the system. So you have to be consistent. If you decide to map the peak in that way, you map the peak in that way across the whole seismics. You don't change interpretation reflector by reflector. Otherwise, no one understands anymore what you're doing. Okay? What is the problem? Well, the problem is that, as you see on the extreme right, there is an aspect that you cannot solve by having only petrelli, only the seismic kingdom treat or whatever you're using. The color is a question of basically, if you want, is an assumption. We assume that red is the peak and blue is the trough. Fair enough, very easy. Once you know which is being the use during the acquisition is fine. The problem on the right is that how you interpret the peak and the trough. Now, we are going to see when we are going to do the pre-stack processing that when you are processing the seismics, the first one of the major requirements now is just to reprocess the seismic by fixing or imposing to the whole single trace that you are stacking a zero phase trace. So I'm assuming that all the traces need to be repositioned in such a way that the peak of the trough is perfectly aligned to what is it, the surface that defines the contours of impedance. How you do that? Basically, zero phase implies that the peak of the peak is exactly at the place where you get the contours of impedance. It's not always like that. The only way to test it, you need to have a well. You need to have a well, you use the well and the sonic information of the well, and you see if the sonic information are basically consistent to what you see in terms of the peak of the trough in your seismics. Because another option, situation you can have, in a situation like that, in which the peak and the trough are not coincident with the contours of impedance, but they are shifted, dephased. So your peak is just within the package and not exactly at the contours. And that's complicated a little bit of interpretation, because then when you are mapping the peak and the trough, you are not mapping the contours, the surface that is defining the contours of impedance, but you are mapping the surface, the package itself. And the only way to test if we are in that situation, is to use a well log calibrated to the seismics, in which you test if the variation of the sonic, if the variation of the density, you calculate or you create, for example, what we call a forward model. To a forward model, you create your artificial reflectivity. If your artificial reflectivity gives you a result using the core information, that one, it means that your seismics has been zero phase. Otherwise, if you are in that situation, the seismic hasn't been zero phased, then you have to be careful, because then the peak doesn't correspond to the place where you have the contours of impedance surface, but it's shifted by kind of 90 degrees. Okay? That's an important steps you need to do, and it's called the QC of your seismics, quality analysis of your seismics. You go and check if it is, which is the convolutional model that has been used, if it is European or American, and then check if it is zero phase or not. As far as I know, in the last 5-10 years, most of the seismic that's been basically processed are zero phased. So unless you are working with a very old seismic data set, okay, or very weird people that have not zero phase or seismic reprocessing, but you have to check, because you never know. Okay? So, this is the practical aspect of the contours of impedance that we have seen so far. How do we play between density and velocity? How do we use, in practical way, our exercise? What I will show you now is a kind of very simple exercise that can be potentially an exercise you can find in an exam, for example. And is a kind of simulation of a forward modeling which I ask you to calculate, given some density and some velocity from a sonic log and from an amplitude. Oh, sorry, from a sonic log giving you the density and the sonic velocity, okay, or the slowness velocity. Usually the sonic log are giving slowness, in the inverse of the velocity, to calculate reflectivity parameter of the various units that you got. So predict what you expect to see on the seismics. Very easy in reality. Now, the first things that you know already, because Jeff has been introducing you, is the Gardner velocity that apply more or less between shale and sandstone. If you apply the Gardner laws for other stuff, it's a good approximation, but not necessarily that good approximation. So as soon as you got in salt, rock salt, anhydrite, limestone, dolomite, and so and so. This is a diagram. It's a logarithm of a book density versus logarithm of the velocity. So a log-log diagram. And it shows you, in black you got the point that has been plotted by measurement done on the field by the well-site geologist, in which is plotting basically the value of the velocity of the book density that is measuring using the well information. It's plotting in a diagram. That curve is the curve that Gardner law is predicting. Now I wrote that curve in 3 different ways using 3 different units. Now, British usually use that one because you think as a feet, isn't it? You still use feet over second. Rest of Europe use kilometer over second and or meter over second. What is important is that the relationship tell me that there is a density is proportional to the velocity variation across the various units, especially between sandstone and shale. That's the way where it better approximate is in the function, exactly separating the two linear properly behaving of the function. Those ones are already departing in terms of linearity. Those ones are departing clearly from the linearity, so doesn't work. And sometimes if you don't have anything else, you have to use that one. And it's proportional to a 0.23 that is a factor of conversion between feet and meters. So is 0.23 if you use the feet, is 1.74 if you use the kilometer, is 0.31 if you use meters. Multiply the velocity of the P wave under root 4. So potence of the power of 0.25. Is equal to what? 4 of VP. Right? But if you got basically calculator, that will do. Okay? Because you got any number elevated to x of the power, you put 0.25, you have done. So you will need a calculator to do that. You cannot do by mind, by memory. Unless you are a kind of Russian that has been educated to do the proper calculation when you were a 5-year, 6-year-old, that's fine. I know. Right. That's how the relationship between them. Now, this relation is an approximate average of the relation of a number of sedimentary rocks type, but is not intended to apply to every single lithology. But in desperate case, well, it's the things, it's most the easy peasy things you can use. So basically, this is a diagram from Castagna that has been the guy working a lot, studying a lot on the physical properties of P and S wave across different types of shell sandstone. It's the guy that developed the AVO method in the last 25 years. And that's the density, is plotting all the triangles that are the sandstone and the square that are the shale. As you see, they more or less follow the figure of the Gardner law, pretty much within a range between 2 and 2.5, and within a velocity between 2 and 5 kilometers. So it works also within compaction condition. It's not that bad. It's a good approximation of your curve. So what I'm telling you is that if you got sonic velocity from your basically, log information, you can obtain the density by using the Gardner law. Quick and dirty. Some case, you see, if used for coal, so shale, sandstone, dolomite, limestone are okay, salt, coal, anhydrite, not the best place where to apply it, okay? Now, exercise. What you got on the left is a classical sonic log across in a series of units. As you see, you can recognize pretty much, this is is in feet, so you're all happy. It's in feet in there. Is a transmissivity value is given microsecond over feet, and you know already the microsecond over feet. You need to transform it because it's a millionth of a second, and then it fits to basically 2 meters. 1 foot, 0.3048 meters. Okay. It's funny because the foot has been introduced by the Romans. But in Italy, we lost completely the Italian way of measuring. The British still preserve it. Basically, it's a passage between an empire and another empire, and they keep the original length. Interesting. Things change. Now, what I put in this diagram is basically the change. Well, let's read what is the exercise, but it's much more easy to read it. It's a record of sonic log in the North Sea, and it's separating the chalk, marl, and sandstone units. It gives you the variation of the transmissivity across the depth. Now, as you see, as you expect, the transmissivity is changing quite quickly across the depth. So what I'm asking you is to estimate, or draw a mean line, use the sonic log to give an average transit time of the geological unit by drawing a vertical line through the average position of the log at each of the 3 units. So you have to draw a mean line through the log of the marl, the chalk, and the sandstone, read off the average transit times for the interval, and use that to calculate as the velocity, as the interval velocity of your various units. So basically, chalk is more or less is there, and the velocity, mean velocity is that one. The marl, the mean velocity is that one, and the sandstone, the mean velocity is that one. The marl and the sandstone have slightly different velocity. They are not exactly the same. Then the middle is stay between 80 and 90, and here the middle is stay around the 90. Okay, and this is a velocity again between 60 and 70. Okay, roughly. Oh, you will get a little bit slightly different value. I don't care about that. If this is, as soon as you define me which is your value, I will get stick on the value that you got in the exercise, and I will use your calculation. Okay, unless you do a mistake on calculating it, but it's almost impossible. Okay. So draw a mean line through the log for the marl and calculate the interval. Now use the velocity to calculate the density using the Gardner laws. The next step, C, calculate the acoustic impedance for all 3 units. You got density, you got velocity. Calculate the reflection coefficient. You got now the all contours of impedance of the unit. You have to calculate the reflection coefficient. That is the ratio between the reflection and the incident. So A1, A0. But A1, A0 is nothing as the rho 2V2 minus rho 1V1 over rho 2V2 plus rho 1V1. You got the rho, that is the density. You got the velocity of every unit, because you calculate through that and through the Gardner laws. You got everything. And then see which kind of reflection number you got there. So, calculate the velocity. Now, I calculate for the chalk a value of 65 microfeet over second, microsecond over feet, okay? I calculate for the marl a value of 85, okay? It's between 80 and 90, and I calculate for the sandstone something a little bit bigger than 90, that is 91, okay? But I can be 92, 90, or whatever, but those are the values that I chose for the exercise, okay? I do the transformation, and I transform it in terms of velocity. I want to see a velocity in terms of meter per second. So what I do the transformation. I transform my microsecond over feet into second, so I have to multiply basically by 10 at the power of 6. Remember, in micro is 1 millionth. Okay, so to go from 1 million to microsecond to second, you need to transform and multiply by 10 at the power of 6. Multiplied by the factor that transforms the food to the meters. And then we got the velocity in meters. So for the choke I got 4,689.23, for the Mars 3,585.88, and for the sandstone 3,349. Okay? Is this clear? Now what I've done, I've transformed the microsecond over feet into a meter per second. I rewrote basically the velocity, the slowness in terms of velocity. Is that fine? Good. Now I have to calculate the density. And what I calculate the density, I got the velocity, because the velocity is the one I got in there. And for each velocity, I'm calculating the correspondent, basically density that I got. So I multiply basically, I use, as I'm in a meter over second domain, I use the 0.31 multiply the VP at the power of 0.25. The velocity, the power elevated, the power of 0.25 of the velocity of the choke give me that value. Of the Mars, give me that value. Of the sensor, give me that value. Multiply 0.31, I got the density of 2.565 grams per centimeter cubed, 2.398, 2.358. So it's telling me a couple of things already. That the one on top got the density that is bigger than the one below. And the one on top got a higher velocity than the one below. So what should you expect in terms of contrast of impedance? Something is going to be negative at certain point. Because the density, the velocity is slowing down the more I go deeper and deeper. Question C, acoustic impedance. Now, here I wrote the equation in which you got reflectivity value, that is A1 over A0 is by definition the reflectivity parameter, is equal to the difference between the contrast of impedance of the object that is on top, means the contrast of impedance below, means the object that is on top over the summation of the two. We already obtained this formula. And you have to do that for the all units that you are analyzing. So for the choke, sandstone, Mar, choke. Okay? So you need at least calculate at least twice, at least 3 parameters for the 3 surfaces that you need to calculate. And the first thing you have to do to calculate the contrast of impedance in sandstone. We got the density from the Garden laws, we got the velocity from the transformation of the slowness parameter from the sonic, and here we go, we got the contrast of impedance for the sandstone. We got then the contrast of impedance for the Mar, and we got the contrast of impedance for the choke. Okay? So I'm just applying the formula as I'm using it. What I need to know, I need to calculate now the reflectivity parameter. The reflectivity parameter, I got 2 reflectivity parameters. Remember that the 2 reflectivity parameters are choke Mar and Mar sandstone. Those are basically the 2 reflectors which I want to predict which kind of brightness of value in terms of reflectivity I should expect to have. Good?
Sorry, how did you know to use the chalk to your marl and then your marl to your sandstone? How did you know to use the marl as your...
Because I got the density of the Mar, I got the density of the velocity of the Mar, I got the density of the...
Is it just because it's in the middle? I don't understand why you're using your marl as the one you're going to calculate it over.
Because I need to understand, I need to calculate the reflectivity between choke and Mar and sandstone.
Is it just because the marl's in the middle you're doing it off?
Yes.
Yeah.
Ah, yes. Ah,
yeah.
Okay, yes.
Okay.
So, now that I got all the contrast of impedance, I'm calculating A1 over A0, that is basically the ratio of the one on top and the one below, so following there, choke over Mar, choke over marl. That one. So the marl is the one below, the choke is the one on top. And I got a negative value of 0.16, as I expect. And then I got basically the sandstone. The marl of the sandstone. I do exactly the same story. In that case, I got the marl over the sandstone. And that's what I obtained, minus 0.4. So it's telling me that the contours of impedance, given the density I calculated with the Gardner laws and the contours of impedance, the sonic log information I got, chalk marl reflectivity is a negative reflectivity. Marl sandstone is a negative reflectivity, but with a lower amplitude or reflectivity respect to the one on top. One on top was minus 16, the other one is 0.4. So that one is almost invisible if you want. That one is going to be the most visible. So that's the way you need to proceed to calculate basically, using the contours of impedance, using information from your sonic log and the formula of the Gardner law, or you can simulate what you should expect in terms of reflectivity. And that's something you can do easy peasy every time you got a seismic line. Well, you can do it by hand. You can do your simulation just to estimate if what you got makes sense or what you see on seismics. There are software that are doing it basically now automatically, but you need to check that what you got, how the output you got is correct, and the only thing you need to check is all these kind of steps. Okay, so it's not that complicated. I'm just using in a practical way. Yeah.
Sorry, I missed that. Is the even though they're both negative, would the marl sandstone one appear positive because it's got a lower? No.
Let me say like that. Even they are both negative, the value that you got in one case is bigger respect to the other one. So it's brighter.
Okay.
Now you have to keep considering, if you want, two things: the number with the sign, and the sign is telling you if it is positive or negative, and the number itself that tells you how much is the difference between the two basically components that you are analyzing. The bigger it is, whatever is the sign, the stronger is the amplitude or reflectivity, sorry, that you expect to see. The sign is telling you if the reflectivity is a positive polarity or a negative polarity.
So would they both be the same color in the seismic?
Absolutely, yes. They will have both a kind of, if you want, blue, depending if you are American or European, a kind of blue or red. But one will be brighter, the other one will be a little bit slower. Yeah. Good. Right. Now, that's closed the topics. We close now the topics of the contours of impedance. So, do a recapitulation of that. We have seen how we calculated the contours of impedance. We started from the big picture in which we know that as soon as you have a generic reflection of the P wave or S wave across a discontinuity, it produces a plethora of change of mode as P reflection and change of mode as P transmitted. But we know, by the example I've given to you, that if you're working in a realistic seismic, basically, acquisition, most of the angular incidents are within 1 degree, 2 degree, 5, maximum 10 degree. So this implies that's probably the theoretical precise way of considering the incidents can be approximated to a kind of almost orthogonal condition. And we have seen that the almost orthogonal condition, the whole change of mode disappear. And what you can basically consider as the main factor are simply the reflection of the P wave and the transmission of the P wave. Given that, what we have done, we have tried to apply the condition that the physics is telling us it's working. So when you do an experiment, you are shooting basically to an air gun or to an explosive, you're creating your source, you are shooting it, it's producing P and S wave. The P and S wave are reflecting to the soil. When they're reflecting to the soil, usually in the instant which they are reflecting, they are producing transmitted and reflected waves. The transmitted and reflected waves are instantaneously produce but they don't create any holes or any breakage of the surface because the wave doesn't have enough pressure to do that. So what is in telling me is that the kinematical condition of what is on the air or on the top units where the incident is coming from with the unit that is below are preserving the kinematic boundary condition of continuity. So we apply that kinematic condition and we obtain that roughly, if we simplify everything, we obtain that A0, that is the incident wave, minus the reflected wave, is equal to the amplitude of the transmitted wave. Then we wrote the boundary condition of the energy. So stress equal elastic parameter multiplied the strain. We know that the strain can be represented through the vibration, and the vibration is nothing else than the wave equation. The derivative of the vibration is the displacement, and so the derivative of the vibration is the equation that we use. It was the cosinus of the blah 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 that we got. What we did, we know that the energy is conserved between the incident, basically ray, the transmitted and the reflected, because during a reflection, what I'm missing through the transmission needs to be preserved in the summation of the whole basically system that I got. Energy needs to be conserved by definition. So what I need to do, I need to write this equation. I wrote this equation, I simplify everything, and using the kinematic condition A0 minus A1 equal A2, I got to the final solution in which reflectivity can be described in terms of a difference of contrast of impedance divided by the summation of the two contrast of impedance. We have seen the scenario, can be zero, can be positive, can be negative, and help you to understand if it is a bright positive spot, bright negative spot, or a zero, basically reflection, which it means that you got everything transmitted. And we apply all this kind of exercise in a practical way. So using a density, or using a sonic log, using the Gardner law, you can obtain approximation about the density, and you can calculate or estimate, if you want, your contrast of impedance value. Okay? So now we know that the reflection that you see in a stacked seismics are somehow related to this kind of beast, to the kind of contrast impedance, and you can start to interpret the variation of the amplitude because of the reflectivity relationship in terms of reflectivity or contrast of impedance. Easy. Now we have to move and change argument and change topics, because our problem is what's happened if I got a multiple reflection. So I got a reflection in one layer, then I got another layer, then I got another layer. The point of view we are going to tackle these kind of topics is we are going to put apart the contrast of impedance for now. And what we are going to do, we are going to look if you can estimate just the velocity up to now. So just the velocity, we can predict the velocity of a ray that is incident into a surface at a certain angle. An incident at a certain angle, what is the velocity to expect coming out from another angle? So if I'm shooting with a seismics a series of rays at a certain angle in a multi-layer, what should I expect to be the arrival of that ray to a certain geophone, and which is the angular relationship between the reflected component or the transmitted component respect to the original information that I got from the source. So we have to move back to geometry, and we have moved back to the geometry using the relationship of reflection, refraction, and transmission. Now, before we enter to the topics, I just remind you a couple of things, because probably we will use it quite a lot. The concept of sine, cosine, and tangent. Just to refresh the mind. You never know. This is the angular relationship between the two sides, the opposite side to the angle, same side of the angle, and then the hypotenuse. All this kind of relationship, I'm not going to go through them. They come from the Greeks, basically, school of Euclid and Pythagoras. Those ones invented, developed all the relationship about that. What we need about that is just the practical use of that. We know that the sine is defined as the side opposite to the angle divided by the hypotenuse. Okay? Cosine is the side adjacent to the A divided by the hypotenuse. That's the definition. use it as a definition. The tangent is the side opposite over the side adjacent. Sinus over cosinus. Another thing you need to write is that the cosinus square plus sinus square is equal to 1. Not written in there, but something you have to write on your books. Remember, cosinus square plus sinus square is equal to 1. So that you can transform the cosinus to sinus. So sinus square is 1 minus cosinus square. If you do the sinus, under root is the root of 1 minus cosinus square. And the way around. Good. Let's start from the basic principle of the reflectivity. When you speak, this is called, that part of the seismology is called ray tracing. So what we are doing now is the ray tracing analysis of any kind of reflection of surface that got a certain amount of contrast of impedance. We know that the direction of incidence, reflection, and refraction propagate along the same plane normal to the interface. So we can describe the problem in a planar view. In our piece of paper, we got basically the distinct continuity, the incident angle, and the reflected and transmitted. They can stay on the plane of a page. We know that sinus of incident angle is equal to the sinus of the reflected angle. That's the first law that you need to fix in your mind. If you are in a reflection, the sinus of basically of the incident wave, the angle of the incident wave E is equal to the angle of reflected wave through the sinus. The ratio between the sinus of the incident angle and the sinus of the refracted or transmitted, so I call it T, to avoid the confusion with the reflected, is proportional to basically the ratio of propagation velocity within the two media. And this is called the Snell laws. V velocity 1, where the incident angle is coming from, divided by the velocity 2, is equal to the sinus of the incidence and the sinus of the transmitted, so the one is propagated below. This implies that if you rewrite this equation, okay, by putting the velocity 1 over the incident angle and the sinus transmitted on the other side, so this is always true, the ratio between the incident angle of the sinus of the angle of the incidence over the velocity 1 is equal to the sinus of the angle of the transmission over the velocity 2 in which is transmitted, and this is a constant called P, and that quantity is called ray path parameter. So if you know those two parameters, you can calculate the ratio of any other transmitted component of your history. And this is valid for V1, V2, V3, V4, V5, Vn, V6, Vn. So there is a ray path parameter constant that remains preserved across the transmission all along the system. Okay? I'm going to skip that, but it's for your information. Why does Snell law work like that? Why the sinus of the angle incident need to be equal to the sinus of the reflection incident? This is a demonstration on it. I'm not going to lose time. You can see for your pleasure if you like. But what is on the back of the Snell law is the principle of the Fermat. Fermat was a French mathematician that demonstrated that the shorter path to get from a point to another point is the path in which the distance A to that point to B, whatever it is, we don't know, it's a generic distance, need to have the derivative of that distance equal to 0. So if you write the equation of that side and the equation of that side, using all the coordinates, you put the derivative to 0, you obtain that the consequence of that kind of limit, that the whole distance between the transmission of the ray to two points need to be the minimum path, imply that the sinus of your angle need to be equal to the angle of reflection. So the angle of incidence need to be equal to angle of reflection. If sinus of the angle is equal to the sinus angle R, it's implied that angle of incidence is equal to the angle of reflection. So that's why the Snell law got this kind of relationship between the sides. It comes from the fact that that law is stating and following the consequence of the minimum path. Good. You know what is a sinus, you know which is the ray path parameter, and you can use it in an experiment in which I'm shooting seismics, and I'm looking what's happened and a ray path that is incident at a certain angle. To clarify, we are using the approximation in which we don't have any change of mode. Okay? So far, so good. We are using only the P wave exercise. We don't care about the change of mode. So all the experiments we are going to see, the figure we are going to see, there is only the P wave playing it. Because despite the angular incidence, despite the look like with a certain angle of incidence, we are basically transferring to reality those angles are very small angles. Okay? So there is no change of mode, and we are looking at every time you got a reflection, you got only one P reflected or P transmitted. Fine. Okay? Now, what I want to do, I want to try to see if I can express the distance when I expect a ray having a generic incidence reflecting to the surface Mn, when I should expect to see coming back. So where I should place my geophone R, at which distance should I place it to track that kind of generic ray that is incident in the surface? Second question, when should I expect to see in terms of time? So if I shoot my experiment with a certain angle, when should I expect that kind of geophone to be able to register the reflected one coming out? The same apply if I got a multiple surface. What's happened to that one? When should I expect him to come out? Where should I place the geophone in order to get that? And at what time it should come out after the second reflection? Now, back to the basic trigonometry, pure trigonometry. So it's nothing complicated things. This is the things that we know is come from the Snell law. So sinus of beta angle, so the beta is the angle that you see here defined, is equal to the sinus of the gamma angle, that is the one of the transmitter. Sinus beta over the velocity 1 is equal to the sinus gamma of the velocity 2, and is a constant p. That's always true. It's coming from the Snell law, okay, between incidence and transmission. Now, let me write the tangent. The tangent of beta is nothing else by definition. The tangent of beta is nothing else. We know that distance over that distance. That distance, that side, is nothing else than the thickness of my layer. So it's something important. It's an information I want to know as an exploration geologist. That component of that one is the piece of the path projected along the trace between the source and the receiver. By definition, my tangent of beta is, by definition, the sinus of beta over the cosinus of beta. I rewrite my sinus of, I keep my sinus of beta, I rewrite my cosinus of beta as the root between 1 minus sinus square of beta, because I know that cosinus square plus sinus square is equal to 1. So, what I got is that the sinus of beta, that is exactly that one, I can rewrite it using the Snell law as a V1 multiplied P. V1 multiplied P is my sinus beta, divided by what? Root of 1 minus the sinus square of beta, but if the sinus of beta was V1P, my sinus square is V1 square P square. So I rewrote the tangent of my angle, function of the velocity, and of ray tracing P pi. Right. What I've been doing, I've been just substituting to the tangent, to the sinus, to the cosinus, the real value of it in terms of velocity using the Snell law. Nothing strange. So what I've done, I basically redescribed the tangent beta and the tangent of gamma in function of their definition, sinus over cosinus, sinus over cosinus, blah, blah, blah. And that's the way you rewrite the tangent in terms of the velocity of the ray tracing. Nothing strange, just a substitution of parameter.
Sorry, is P or rho? Is that separate to V1?
P is that P.
That P there, so
Yeah.
this is completely different to the V1 row 1 thing.
Pardon?
You know the other equations where it's like A equals row 1 V1 and stuff. This is completely different to that.
Equation for acoustic impedance is rho 2 over V2. You know.
Yeah. But it's a rho, it's not
Rho
a
and
P.
P look very similar.
Yeah, but rho and P, rho is rho and P. So.
Yeah. This is a P.
Yeah. So, I'm using different letters, there are different options. Now, told you now the contours impedance is a chapter closed. Okay? Chapter closed. Now we're looking at different things. Closed, done, we have seen how we can use it. Now we can move on to another aspect, that is the reflection in the multilayer. Good. Now, where is the physics of that? Because now it's only a redescription of my tangent function of the velocity of the ray tracing parameter. The physics of it comes here. What I'm telling you is that the distance between the source and the receiver can be expressed in terms of the path that is done by my ray during the multiple reflection in such a way. Now, if I want to express basically the portion of x done by this path, I have to write that the tangent of beta, that nothing else that the distance, the piece of the distance of my x, divided by my h1. Okay? That's the definition of the tangent. The tangent is that bit divided by that bit. But that bit is h1, the thickness. And that one is the portion of x, that portion of that is defined by the ray path that is transmitted in there. Then there is the other bit of the ray path that is transmitted in the second layer, that is in projection represent the other bit of the distance. Okay? And the other bit of the distance is nothing else than the tangent of gamma, that is, again, that bit in there, divided by h2, that is the thickness of the second layer. Now, that's half of the whole path, because I know by the Snell law that the angular alpha is exactly angular to the reflection in there. Alpha is equal to that one. And gamma is equal to that one. Okay? Still valid, is still Snell law valid. Now, this implies that I just have to multiply twice that piece to represent me that piece as well, and that piece as well. So that's where it comes from. Twice h1, the tangent of beta, for that piece and that piece, and twice h2, tangent of gamma, for that piece and that piece. So now I rewrote the distance along source and receiver, function of the path done by the ray tracing. Done. Now, as I don't know basically the angular, because I want to express my angle, because I don't know the angle, I cannot measure the angle when I'm doing an experiment. The only thing I can measure is the velocity. But I know to rewrite the tangent in function of the velocity of the ray tracing parameter. So I substitute my tangent vet, that kind of solution. So 2h1 multiply v1p over the root of 1 minus v1 square p square, that's piece, and the tangent of gamma, that is exactly that piece, I put it in there. And that's the distance. If I know the velocity of the first layer and the thickness of the first layer, I know the velocity of the second layer and the thickness of the second layer, I can predict where I should expect the ray to coming out along the surface, where I should place my geophone in order to track it. Very simple, very easy. Pure trigonometry and the physics of the Snell law. What is helping me, the Snell law, this is telling me the angle of incidence is equal to the angle of reflection, and that's true every time I got a reflection, except that that angle is different from that angle because that object has a different velocity and thickness than that object. So, but incidence reflection still valid, and that's why they help me to calculate all the procedure for half of them and then multiply by 2 to get the other half of them. I'm allowed to do that because of the Snell law. How do I express that in terms of the time of arrival? Well, that's a distance. So to get the times, by definition, velocity is space over times. So times is the space, my x, with all this kind of stuff, divided by the velocity. Here we go. That one is not inertia. All that stuff in there divided by the velocity. Okay? That one in there is representing basically a different way of writing that one by using directly the function that is the time that is taken to get there is literally the times of a ray that is doing that path and that path. Okay? That path is exactly the hypotenuse of that layer and that layer. So to get that hypotenuse, I need to use, for example, the cosinus of that, in which is that one divided by that one. And that's my new Sn. So if the cosinus of beta is the h divided by my hypotenuse is basically my h1 divided by my cosinus. There. My h2, that one, is my h2 divided by cosinus of gamma. There. So that formula, that formula are perfectly equivalent. You can choose whatever you want to calculate those. That one is equivalent to that one. How you can see that? The cosinus bet is in relation with the sinus. The cosinus bet is that one. So it's 1 over sinus squared bet. This is 1 over v1p squared. That is 1 over v1p squared. So everything matches. Okay? So what I'm telling you is that if I ask you, I've got an explosion happening in a certain place of the area. I know from the wells that I got some kind of unit, 2 units that got a thickness h1 and a thickness h2. I got an information from the sonic log about the velocity of the unit 1 and unit 2. Can you calculate me at which distance you should expect and when in terms of time you should expect to be able to measure on the receiver there the arrival of a ray trace that they at least a couple of reflection? The answer is yes. You can do it by using that formula or that formula. That one is expressing when you should place the basically the geophone. That one is telling you when you should expect to measure from the timing of basically explosion to see the first arrival of the P wave. Now, you have to play a little bit with it. It's just to play, but you will see it's quite obvious, because in reality, what is driving everything is the Snell law. What allows me to build up all this relationship is the trigonometry that, you know, is that principle. That principle is basically the gold of our solution. It's telling me that I can tell that the angle of incidence is equal to angle of reflection, and the sinus of the angle of incidence divided by the velocity of the medium where it is incident is equal to the sinus of the angle of transmission divided by the velocity where the medium is transmitted. And that is solving all the problem and keeping quite simple. At the end, you don't have that much parameter. How you calculate basically the P? Well, the P is the only information that you need to get out from one information of the angle or the velocity. But in that case, if I give you an exercise, you pretty much understand that. If I ask you where you should place the basically the geophone in order to track it, I need to give you an information about the P. So I need to give you a kind of angle. If I'm asking you which is the angle that you should be doing if you want to track it with a geophone at a certain distance, I'm already giving you the X and ask you to solve with respect to the P. So, in any case, I need to give you at least 2 of the 3 parameters so you get the 3rd parameter. That's most of the exercise. But what you have to be thinking is help you to think which is the distance in which you have to place your geophone to expect to see the reflected wave to come out, do you your acquisition. and help you to understand how much the thickness is affecting the time of arrival of your equation. That's where the thickness comes from. Those are the parameters controlling, as much as the velocity, but that's the thickness effect. So if you change the thickness, and if you remain fixed, basically your source and receiver, what's happened to your ray tracing? What is going to change? Are you going to miss it? You need to place another geophone to track it? So it helps you to think in a quantitative way how you should organize basically your acquisition exercise, knowing how the trace is behaving across the surface. That's a kind of criminal way of writing it in terms of mathematics. I'm telling you, quickly simple, that you can apply the time formula that you got for any type of reflection, an infinite number of reflections. So if you to write that equation for 25 layers, you will have first layer 2 times the thickness of the first layer divided by the velocity of the first layer, multiply 1 over v1 squared p squared, plus the second element, second layer, twice the thickness of the second layer divided by the velocity square of the second layer of the second layer. If you got a third layer, which kind of formula is going to be? It's going to be an h3 twice h3 over v3 root 1 minus v3 squared p squared. If you got a fourth layer, it's going to be repeated, the same symmetry, the same object. An abridged way to write it is that one. K can be 1 to infinite. And the same for the x, can be 1 to infinite. So it's the summation of any sort of layering from 1 to n of n number of thickness and number of velocity of the layer that you are doing the summation. So that's the powerful things of that formula, is that you can apply it for 2, 3, 4, 5, 6, 25, 20, 1,000 layers. And it predicts you what you should expect to see. The P wave coming out in the receiver. In the exercise that usually we are going to do, we don't play with more than 2 layers because it takes you time to do the calculation. We are not machine, we are not computer, okay? It's not an exercise how much faster you do the calculation. It's an exercise if you understand what you are doing. Okay? The distance that you should expect to see in an exercise like that. Now, food for thought. Let's touch a little bit. The only real information you have during an acquisition, so when you are acquiring a seismic data set, what you really get from the whole equation we have seen before are the offset, because that's the one you can choose. You can choose how you place your geophone. Okay? No one can, I mean, you can choose it. You decide where you put the source, and you decide where you put your own. So you can decide the x distance. The offset is nothing else than the x distance. That's the offset. What you know is the time of arrival at various geophones. So what you know, because you can measure it during your experiment, is the x. So what you can measure is that value. So you know that value, and you know that value when you do an acquisition. What you have to work out is that stuff. You can deduce one thing. You can deduce the tau zero. My question is how and which test you need to do. Tau zero is defined, so I introduce you now the tau zero, is nothing else than the times of a ray that is traveling perfectly perpendicular to the two surfaces. So it's doing a path that is exactly the H1 path, way and back, two-way travel times. My question is how you can obtain this information.
Smoke. Sonic?
You can get from the sonic. If you don't have any sonic, how you can use just a geophone and the arrival of a P and a surface wave. Now, remember what is this, because now what I've shown you is the P wave that is reflected. But which is the typical path of a surface wave or direct wave? Path. Path. So a direct wave is doing exactly the path without any fussy geometry, directly from source to receiver. If you know that a direct wave is doing a direct path between the source and the receiver, you know that the time that is taking to cross the offset gives you exactly the velocity of the wave. But the velocity of the surface wave is a little bit different from the P wave. But if I give you the factor of transformation between surface wave and P wave, and you got books that can give it to you, you can obtain from that the velocity of the P wave for the first layer. If you got the velocity of the P wave of the first layer, obtained by calculating straight and simply the surface wave moving through S to R, then you got the velocity of the first layer. Well, the only thing you need to have is the time of arrival of a perfectly orthogonal tau zero ray. So the ray that is traveling perfectly orthogonal is coming back, is doing exactly that thickness. Because what is the problem of that ray? That ray is traveling, as soon as you are inclining that ray, is doing a travel path that is proportional to the thickness, but it's not the thickness. It's bigger than the thickness. The only thickness is the only ray that is doing the real thickness of that is the one that is orthogonal to that one. Bang, bang, and that one, and that one. Now, if you know the velocity of that one through the surface, velocity, and you got basically time of arrival because you can measure it on a geophone that is a zero offset with respect to the source, then you got immediately the thickness of the first layer, the velocity of the P wave of the first layer. And then you got some parameter in there. You can start with some parameter like that one, you can start that parameter. The other piece is controlled by that bit. As soon as you define the angle you expect to have, any angle should respect that relationship. So an angle divided by velocity 1 need to be equal to any angle of transmission divided by velocity 2, and you can find the velocity 2. So everything is linked somehow, so you can obtain some information. Every time I will give you an exercise, I will give you enough information to get out from there. So, and we will never move for more than 2. I mean, we can use 3 layers, but only 2 discontinuity. Because as soon as you enter to the 3rd discontinuity, it starts to be quite a complicated calculation and timing. Spend time on that. It's not an exercise about you are fast on doing calculation. I don't care about that. I don't care about if the result you get makes sense. Okay? We stop in there. Okay, what I will do, I will upload some exercise this afternoon, so you can play with. And on Monday, we start with the correction of those exercises. Okay? Think about it. Yes. What problem at all?
Sì, sì.